To calculate the power components in the singleton AM, let us consider the time domain equation for the singleton AM here. S of t it is AC cos 2 pi FCT plus AC mu by 2 cos 2 pi FC plus FMT upper side bantam, and then lower side bantam AC mu by 2 cos 2 pi FC minus FMT. So we got these three components in the singleton AM, that is carrier signal, upper side bands and lower side bantams. Let us consider the power component due to each component here. So this is what the carrier component, this is upper side band and this is lower side band. So that the total power of AM we can take it as the sum of carrier power and then upper side band power and then lower side band power. So let us consider each power of these components. We know that the power of some A cos theta or A sin theta, we have that power is equal to amplitude square divided by 2. So independent of the frequency and phases, we have the power of a cos or sin signal is equal to amplitude square divided by 2. So here first signal amplitude it is AC, so that carrier power it is AC square by 2, and upper side band if you see it is having the amplitude AC mu by 2. So let us take amplitude square AC square mu square by 4 divided by 2, and then lower side band it is having the power component that is equal to amplitude square, that is AC square mu square by 4 multiplied by 1 by 2. Let us further simplify this expression by taking AC square by 2 common, so that I am getting here 1 plus, here it is mu square by 4 and then here also mu square by 4. Further we can simplify this expression by taking AC square by 2 is nothing but carrier power here. I am writing as carrier power PC, and then 1 plus this is equal to mu square by 2. This is very important formula for us. Here the total transmission power of an AM signal is equal to carrier power multiplied by 1 plus square of the modulation index divided by 2. So on which factors this total transmission power of AM depends, means this is depending upon two factors, that is carrier power and modulation index of the AM. And from this we can consider that if the ideal case mu is equal to 1, then the transmission power of AM signal should be equal to carrier power multiplied by 1 plus 1 by 2, that is transmission power is equal to 3 by 2 carrier power. Observe the carrier power in the AM signal, that is equal to 2/3 of total transmission power of AM signal. That means 66.6% of total transmission power of AM is consumed in the carrier power. So carrier power is nothing but 66.6% of the total AM power, where the message signal having the total information actually, but the message is consuming only 33.3% of AM, both combinedly LSB and USB. If you observe the power components here, this carrier power we have determined that 66.6%. So the remaining 33.3% that should be equally divided in upper side band and lower side band, means upper side band having 16.6% and lower side band also having equal 16.6% of AM. What we can observe with this analysis, it is generally we want to transmit information with the help of message signal. So for that purpose we are using carrier to modulate that signal for so and so benefits. So because of the modulating that message signal, what we are spending extra means we are spending 66.6% extra power for that carrier signal, even though carrier does not contain any information here. So the total information lying in the message signal in terms of upper side band and lower side band, which consumes only 33.3% of total AM. But the carrier signal that is consumed 66.6% means this is considered as wastage of the power. So some power is wasted in conventional AM signal in terms of this carrier signal this much. So we need some modification for saving this power.